Next, we come to the second law of thermodynamics in this section, and we'll understand it in terms of heat engines. So heat engine is an engine that takes in energy by heat and converts it to another form, okay, or other forms. In general, heat engine carries some working substance through a cyclical process. So there's a gas which maybe expands and then contracts and expands and is compressed in a cyclical fashion. That means it's going back to the same state it started from, right? So it's coming back to the same internal energy as it had at the start, which means delta U has to be 0. Yeah? Energy is transferred. So let's say here is my heat engine, this green thing, and it's going in a cyclical fashion, round and round. It's taking in some heat from a source, okay? So Q in, here's a reservoir of heat. It can continually provide heat. Okay, here's a sink. That means if this throws out heat, this can keep absorbing it, okay? And the engine will do some work. Okay, so energy is transferred by heat from a source at a high temperature. This is the energy transferred in. Work is done by the engine, so that's energy going out. And energy is expelled by the engine to a sink at a lower temperature. So there are two things out, there's one thing in. Yeah? The process originates and ends at the same state, so U final is equal to U initial, okay? That means it's an isothermal process, yeah? And Q must be equal to W from the first law, yeah? So net heat in or out must equal net work with a negative sign. Net work done per cycle by the gas is equal to the area enclosed by the path, representing the process on a PV diagram. So remember, the work done was the area under the curve in a PV diagram. Here, since let me just, sorry, let's go back. Here, because our, let's sketch a rough PV diagram. Okay. Now, my process starts at some state, and it's going to do some cycle type process, and it's going to come back. It doesn't have to be exactly a circle. It could be any shape for the path, but it needs to come back, right? So my U, this is my internal energy here, equals the final, okay? What's my area under the curve? It's all this shaded area. It's the area inside the loop now, okay? This is going to be my work time. Okay. Okay. So exactly the same diagram. Heat engine absorbs heat from the heat reservoir, which might be some fixed temperature TH, takes in an amount of energy equal to QH, does work W engine, okay, and gives off heat to the cold reservoir, which is at some temperature TC, okay. Here's that PV diagram, drawn much better than I did, okay. So we can define the thermal efficiency of the engine, this heat engine, as the work done by the engine divided by the heat that it took in. And we want just the absolute value of the heat, so we're not interested in the positive or negative signs here. We know from conservation of energy that the work done must be Q in minus Q out, right? So QH minus QC and divided by QH. So these two are going to cancel to give me 1. That leaves me with 1 minus QC over QH, absolute values. To have 100% efficiency, we need E equals 1, right? That means this term must go to 0, which is not going to happen. It'll only happen if QC is 0. That means no heat goes out at all. All the heat in QH is used to do work. And you will find that that never happens. That's the second law of thermodynamics. So we can never reach 100% efficiency. So let's do a simple problem based on this. expression for efficiency. An engine does 15 kilojoules of work while absorbing 75 kilojoules of thermal energy. Calculate the efficiency of the engine, and you can do part B. So we're just going to use the formula for efficiency. It's the work done. How much is the work? It's 15 kilojoules. Kilo is 10 to the power 3 divided by the energy taking in, QH, that is 75 kilojoules. Actually, since both are kilo, I need not have written it. I could have just canceled it. But anyway, so it's going to be 1/3. Okay. And you are going to do part B. Then you should compare your answers to mine. And this is going to give you 0.2 efficiency. And this is going to give you 60 kilojoules. You might have seen this toy bird which keeps drinking water and going back up, drinking water. It's essentially doing a cyclical process. Yeah. It has a special kind of fluid filled in it, which might be dyed different colors. Okay, and that fluid has the property of having evaporating at very low temperature. So it boils at very low temperature. And what happens is it produces its own vapor at low temperature. So you started off by dipping this in the water. Once it dips, the vapor cools and goes back down. This part becomes heavy. The bird lifts. Then it goes back up because this evaporates again. And the gas comes in here. This part becomes heavy. It goes down. It dips in the water. The gas cools, comes back down. This part becomes heavy. It lifts. And that process seems to go on perpetually. So it seems to require almost no work. However, some work was done in initially starting the bird off. Yeah? So people have been trying to make perpetual motion machines like this for a long time, but you will never be able to make a perpetual motion machine. It will have to defy the laws of thermodynamics to do that. Okay. Heat engines can also work in reverse. That means they can take heat from the cold reservoir and give heat to the hot one. And why would you want to do that? You would do that, for example, in a fridge, okay, where you want to cool something which is already cold. Okay, so this is called a heat pump, okay, when it does that. An air conditioner does the same thing for rooms or houses. Okay, so now what's happening in the heat pump is you're taking in QC from the cold reservoir, you are giving out QH to the hot reservoir, and work needs to be done on the heat pump in order for this process to happen, because this is not a natural process. Yeah. So now notice the different arrows, 2 arrows going in and 1 arrow coming out. Yeah, exactly the opposite of what we had before. And we don't measure efficiency now. We're going to measure something called coefficient of performance, defined as the work done divided by QC taken in. Or QC divided by the work done on the engine. So QC is what we stand to gain, and work was what we had to do. So what fraction did we gain compared to what we had to do in order to gain that? That's our efficiency. Typically, this is going to be some number 5 or 6. It's always going to be a number higher than 1. Okay. So 5 or 6 would make a pretty good refrigerator. And if you use the heat pump in a heating mode, so you have an air conditioner, which is now heating, it's winter, then you are taking in heat from the outside, which might be quite cold, but you are still taking in heat from there. So QH divided by W, okay? So the engine can work both ways. Let's do another problem on this. A refrigerator does 18 kilojoules of work while moving 115 kilojoules of thermal energy from inside the refrigerator. What is the coefficient of performance? So you just need to use this formula here, and basically you're going to get 115 divided by 18, right? There's no point writing it. It's going to give you 6.4. Remember I said 5, 6, you get these kind of numbers. The second law of thermodynamics was given by this man, Lord Kelvin. Okay, and we saw him before when we talked about the absolute temperature scale. So there's no one way of writing the second law of thermodynamics. You may see it in several different guises, and we'll try to understand that. No heat engine operating in a cycle can absorb energy from a reservoir and use it entirely for the performance of an equal amount of work. That means QH can never be equal to W. There has to be QC, which is finite, yeah, in the system that we just studied. So QC cannot be equal to 0. The system must expel some energy to the environment. It cannot use all the energy to do work. That means our efficiency must be less than 100%. Yeah? And this is called the Kelvin-Planck statement. Another way is to think that the second law states that it's impossible for the system, in any system, for heat transfer from a reservoir to completely convert to work in a cyclical process in which the system returns to its initial state. Heat engines are an important application. This is what we've seen so far. Yeah? So here's our heat engine again. We take in some heat, the system does some work, system moves in a cyclical fashion, and it must throw out some heat. Q out. Yeah? So in summary, we've now seen two laws. The first law tells us that you cannot get a greater amount of energy out of a cyclical process than you put in. So delta U equals Q plus W. If you put in Q and W, all you're going to get out is the change in internal energy, delta U, which is equal to those two. Cannot be greater. Or energy cannot be created or destroyed. Energy of the universe is always constant. Okay? Since there's nothing which is outside the universe. So whatever energy we have, that's the energy we have. It can change form, but it can never be exchanged with anything outside because there is nothing outside by definition. And the second law says that you cannot even break even. You cannot even convert all the energy that you take in into work. Yeah? You have to lose some of that energy. So you have to throw out some heat. Alternative system statement for second law. If two systems are in thermal contact, the thermal energy transfers spontaneously from the hotter system to the colder system. This is relating back to the 0th law also about thermal equilibrium. So heat transfer occurs without work being done, i.e. it is a spontaneous process. At this point in your book, there's the Carnot cycle. We're going to skip Carnot cycle, but a Carnot engine is essentially the most efficient engine that one could imagine.